Okay. Thank you very much. Thanks a lot for organizing this workshop. And I'm kind of sorry that I will be breaking this nice flow of talks about geometric flows, but I'm only going to speak about minimizers. So this is joint work with André Guerra, who is in Cambridge right now, and Kostas Zemas, who is in Bonn. And let me write down the functional that we'll be looking at. So we are taking maps from the 3-sphere to the 2-sphere. We have a parameter, let me call it lambda, positive, and an energy, I'm going to call it E lambda, which has two terms. First term is just the classical Dirichlet energy. And then you have this term which looks like that. Okay, let me write it like that. The squared norm of the pullback of the volume form on S2, which we can also write in coordinates. It's just the sum of the of say the volumes indicated by two directions. If you take an orthonormal basis on S3, and here of course this is S3. Just if you don't like differential form, here is the coordinate description. So this is an energy that is called Faddeev-Skyrme because it comes from these models of quantum field theory. So Skyrme introduced it in 61. So for him, it was more for maps from a 3-manifold into S3, and then Faddeev a bit later. So then, of course, if you are into S3, I mean, you need to change a bit this definition. But anyway, I'm just gonna talk about the S2 valued one. And then Faddeev really introduced the one that we are looking at right now. And somehow, okay, to have this term in the energy is quite natural, right? If you are writing down an energy, the Dirichlet energy is the simplest one. And the reason why they have terms like that is because they want to find what they call topological solitons. And so they want a term that will somehow make it possible to minimize in homotopy classes. So that's kind of the whole thing of the story, to find minimizers in homotopy classes. And in fact, this is kind of the question we're asking all along. When you look at map from S3 to S2, you have a particular explicit map, which is the Hopf vibration, which is the first example of a homotopically non-trivial map. And here's my question: can we say that it is a minimizer of this energy in its homotopy class? And I'm gonna give definitions of everything. Okay, so that's the question we want to partially answer here. So let me recall or tell you what the Hopf map is and how can you classify homotopy classes for maps from S3 to S2. Let's start with this Hopf map. So let me call it H. It goes from S3 to S2. And it has an explicit expression, but in fact, it was introduced by Hopf in 1931. And the main point of it is, I think it was the first example of a map from S3 to S2 that is homotopically non-trivial. That's why he introduced it. So this is the first showing that P3 of S2 is non-zero, if you want. Okay, you can give a coordinate expression, which at the end will not play so much a role because I will not go enough into details for it to be useful for you. But still, so there are many ways of representing that map, but maybe the easiest is to view S3 as a subset of R4, which you can view as C times C. And then you take coordinates ZW and C times C, such that modulus Z squared plus modulus W squared is equal to 1. And you just divide one coordinate by the other. So this gives you a complex number, right? And then you do the inverse stereographic projection. So yeah, I'm identifying the sphere we see via the inverse stereographic projection. So it has this very simple expression, and it has this property that when you take two values in S2, you look at the pre-images by this map, this gives you two circles in S3, and have this non-trivial linking number, equal to 1, in fact. That's why you get something topologically non-trivial. Okay. Okay, so now how do we characterize homotopy classes for maps from S3 to S2? This is via this Hopf invariant. So you take a smooth map. So there are many ways of looking at this Hopf invariant. I'm going to give you two ways. One which I find quite enlightening, and one where there is a formula, and this is the one we're actually going to use. What you can always do is write it. You can factorize the Hopf vibration. So you can find the lifting U hat, where U hat goes from S3 to S3. Okay, and then once you are from S3 to S3, you can talk about the classical degree. So this gives you a way of classifying what's going on topologically. So in that case, okay, Q of U would be equal to the degree of this lifting U hat, where you take any U hat that satisfies this. Okay, so here you have to believe me that you can do this factorization. But then Whitehead, I don't remember exactly when, realized that there was also an integral formula for this Hopf invariant, like there is an integral formula for the degree. I'm gonna give it to you in a minute, but just from this definition, you see right away that the Hopf map, it has Q of H equals to 1, right? Because here you just take the identity. And the integral formula that is going to be more useful for us, and where you will see the link also with this type of term, is this one. Okay, so there is a normalizing factor, so like the values are really integers. And then you need to integrate a 3 form, even like that. So, okay, here. This is a 2 form on S3. And it's actually closed because this form is closed. And then it's exact by Poincaré's lemma. So you can write it as D of someone, of a 1 form. So here beta is a 1 form. And it's not so hard to see that this expression actually depends only on that. So any choice of a 1 form like that you make, it will give you always the same value. And in fact, people have shown that this gives you always an integer that corresponds to that in the smooth setting. And okay, and also maybe it's interesting to see that this Q of U is going to be always less than this thing. Up to a constant. This is just some kind of Poincaré inequality. Like you take beta minus its average, and then you apply Cauchy-Schwarz once, you get the beta minus average squared, d beta squared, and then you use Poincaré inequality over beta minus its average. So this is what these people were happy about, that this thing controls the topology somehow. Okay, so if U is smooth enough. Here you would need, I guess, UC1 would be enough to make these definitions and to make sure that Q is an integer when it's defined like that. Everything is fine. And actually one thing that is quite non-trivial that people have already studied before is that this thing, which is an integer if U is smooth, is also okay if you assume that this energy is finite. So basically you need to approximate maps with smooth maps, but it's always quite tricky when you have this manifold volume maps. And this energy is not directly, like, it's not obvious that you can do that thing easily. So there are quite subtle arguments. This is in papers by Fanghua Lin and Yisong Yang in 0407. Actually, at the end, they don't really show this full thing here. And there is a complete proof in the paper by Oakley Kapitansky from 2010. And we actually give a slightly different proof, a bit shorter also in our paper. All right. So that's kind of the setting, and we want to understand this question here. Can we say that the Hopf map is minimal? So let me tell you what is known. Okay, first thing, it is back to a paper by Ward in 99. If lambda is too small, then it's simply not true. So H is actually unstable. You can find small perturbations of H which decrease the energy. If lambda is less than 1/2, okay? So if we want to answer this question with yes, we have to assume that lambda is larger than 1/2. And in that setting, the first thing you can try and do is look at somehow linear stability. So do all perturbations give you an increase of energy? And this has been checked by Isobe, and I guess this was independently by Spate and Svensson. H is actually stable if lambda is larger than 1/2. And okay, here I mean that the second derivative of the energy is positive. So this is like the linearized operator on H, the one you get from looking at perturbations in any direction. And when I write this, okay, actually there are some symmetries of the energy where you cannot expect, where the energy will stay constant. So you can just expect this when you remain orthogonal to these symmetries. Symmetries are basically just rotations in S3. Okay, and another important fact. So, okay, and from this type of information, you can deduce that, say, locally in C1, you are a minimizer. But you see that locally in C1 is not really like a good thing with this type of energy. So this is something I'm going to come back to. In the same Spate and Svensson, a bit later, they realized that basically in the case where lambda is equal to infinity, so if you have just the second term in the energy, then actually the Hopf map is a minimizer in the sense that you have this inequality. You take any U, which is in the same homotopy class as H, and then you can show this. So actually, how does it go is just, this is quite natural. This is just looking at this inequality. This is an inequality between basically quadratic forms on these forms. And so if you forget about maps U and you just look at it as an inequality between these two forms, then those are quadratic objects. You have a linear operator associated to it, and you just, if you manage to do the spectral decomposition, you look at the first eigenvalue, and this is going to give you the optimizer. And it turns out that the first eigenvalue is precisely given by the two form that corresponds to H. So you have to do this, but this works fine. Okay, I'm gonna give you, so okay, when you see that, what you think is at least it should be true that if lambda is large enough, the H is gonna be a minimizer, and this is exactly what we show. But first, let me mention that there is a related conjecture by Rivière. Oh, okay, it's not directly relevant to our result, but it's a beautiful question, so I'm happy to mention it. So Rivière, in a 98 paper, he studied basically minimality properties of the Hopf vibration for a bunch of energies, which are basically the P energies, like integral of du to the P for various P. And one case that is particularly interesting is the case P equals to 3, right? Because on S3, this is the critical case, the one that is conformally invariant. And there, I mean, he was a bit in this situation that he could show the local stability, but not much more. But still, he conjectured that that H should minimize the 3 energy. And in this nice short paper there, he realized that somehow there is a property of H that gives hope to do a kind of min-max strategy a la Wilmore conjecture to show that kind of stuff. So this is what he suggests in this paper. So this is much harder stuff than what I'm going to tell you now, but if you're interested, you could take a look. All right, so let me state our theorem and give you a few words about how we prove it. Okay, so this is from this year. So I basically already told you what it is, but there exists a lambda large enough such that if you're above this lambda, then the Hopf map is minimizing. It's actually the unique minimizer, and when I say unique, it's always modulo symmetries. Okay, so here modulo symmetries, what I mean is that you get not only H, but you can compose with any rotation in R4. Right, so your rotations in R4, they preserve the sphere. And so this is a valid competitor, and actually the energy stays the same. Well, as I said, it's quite natural to expect that this is gonna be true, given that you have this, and also that you have this kind of local stability property. So let me be a bit more precise about why this should be true. So okay, as I said, you want to combine the minimality for lambda infinity with the stability for all other lambda. So why should these two properties give you the minimality for at least for large lambda? It's probably quite clear to everyone. But basically, you need some kind of more precise way of stating the stability and the minimality here. So let me. You need quantitative versions of these facts. So what is the type of stuff you need? There would be a first thing where you would like to say that so this is something we've seen a lot this week, that when you have an inequality, you know the minimizer. I mean, you want to go one step further and understand if the difference between those two things actually controls something, right? So hopefully you're able to control like some function that is strictly positive of the distance between you and this set of H and the symmetries of it. And we would also like somehow a quantitative version of the stability, meaning that we don't want just local C1 minimality, but something that behaves well with respect to the type of distance we can hope to have here. So E lambda U minus E lambda H, you want it to control some function of the distance, again, the same distance. This is if lambda is above 1/2, of course, and if you assume that this thing is already small, right? This is the kind of local stability that you can hope to have from there. But here, one of the important points, and you want this distance here and this distance here to be the same. And it's going to be clear once I sketch, now once you have these two things, how you get, okay, in this row 1 and row 2, in this argument, they could be like any functions that are positive for t, strictly positive. And of course, they will also go to 0 as t goes to 0. Okay, so basically, once you have these two things, I mean, you look at what happens for large lambda. Okay, so okay, given that, so if you have E lambda of u is less than E lambda h for a large lambda, well, you use your fact 1. It will tell you that because the difference between because for lambda large, like the dominant part is the second part, it will kind of force this thing to be small, and it will force this thing to be small. So you will have like the distance between u and h modulo symmetries will have to be small, okay? And once you do that, then you just have to apply 2, right? Okay, and you also know the equality case. So this is like very simple, very basic. You just need to have like inequalities that do this, and the kind of subtle thing is you want these distances to match. So by the way, like the Isobe paper of 2008 gives 2 where the distance is the distance in C1. That's not enough to do something like that because there is no hope that this is going to give you a control. All right, so, and there is another issue, of course, is that here I want this type of stuff to control the distance between u and h. But in fact, I mean, it's only taking this pullback form here. So what you can really hope is that it controls the distance between the pullback forms, but not much more. But this is not so much of an issue. Okay, what I just said is that, I mean, you cannot expect it to work exactly like that. Because this thing here basically you expect it only to control the distance between u star omega s2 and h star omega s2, right? But as I was saying, this, I mean, somehow the fix for this issue is that you do everything at the level of these forms. So this is an idea that was, or I think it was really introduced by Rivière. In that paper I was talking about. Basically, you use just the fact that your du squared So you have all the derivatives. So in particular, you also control like these determinants with it, okay? And there is an optimal inequality. Okay, so you use this. This gives you a lower bound for your energy that is only defined on this two form here. And this is the energy you're going to be working with. And then just at the end, you're going to come back to the actual full energy and try to understand if you have equality here, why it forces you to be equal to the Hopf map. So those are things that are actually pretty well understood. So this functional F lambda is what? It's just basically you take a two-form alpha, and you have twice its L1 norm plus lambda times its squared L2 norm. Okay? And where is it defined? Well, for alpha, which are like two forms on S3, which are closed. And there's that Q of alpha, which would be this same formula as before, just now we view it as a function of alpha instead of as a function of u, is equal to 1, and this is the same definition as before. This is for any one form beta, and again, this does not depend on the choice of beta satisfying this. Okay, so basically you relax. Now you're looking at this problem of minimizing F lambda, and if you can show that the alpha that corresponds to H is the only minimizer of F lambda, then you can come back to E lambda at the end. So what we really do is to show the minimality of what I will call alpha 0, which will be the pullback of the form, from this form you obtain from the Hopf map for F lambda, and then it is kind of standard how to go back to the Hopf map at the level of the energy E lambda of U. I actually don't know when I started. How much time do I have? 10 minutes? 10 minutes, okay. Right, so for a lambda larger than some lambda 0, that has to be big enough, but this is actually, I mean, we didn't do the explicit calculation, but we never use contradiction arguments, so this would be explicit, maybe, I don't know, 100,000. What was? So the lambda 0 we get really from using this step here. Like here we are really using that lambda should be large, so that we can apply this thing 1 that will give you that we stay in a neighborhood of it. And then, okay, this should be large enough so that this small enough then is one that gives you that this is small enough to apply the equality to. Okay, so maybe let me just write down, I mean, the actual inequality, the quantitative versions that we get for the, so I had this 1 and this 2 where I was not very explicit on what rho 1 and rho 2 were. I mean, for this one, I mean, I told you a little bit about the proof, like it's basically by doing this spectral decomposition of this quadratic form here. So it's kind of clear that you will get an inequality, right? You just take the spectral gap and you write this. So this is, you just have to check this, be a bit careful about it. So you take maps alpha, I mean, two forms alpha satisfying this constraint, and then you get this, like, you control the distance L2 squared between those things. Again, I'm always kind of a bit loose on what I mean by symmetries, but you have a kernel naturally, and the part that is slightly less obvious is the stability part. And here again, you can do it with the square distance, the squared L2 distance. This is if this is small enough. Okay, so those are the two inequalities we get. Right, so let me take 2 more minutes to just say a few more words about this thing here. So somehow, I mean, it's if this f lambda were a smooth functional on a smooth space, this is clear that you would get something like that, just because you have the second derivative is strictly positive, so you get something like that, right? So let's say you take a perturbation gamma of your alpha here, of your alpha 0. Right, you write down that this is the second variation. So first alpha 0 is a critical point, so you get no linear term. So you get your quadratic terms, and then you get a bunch of other terms, right? And what the positivity is telling you is that if your perturbation gamma was orthogonal to this kernel of this thing, then this is actually controlling like the L2 norm of gamma squared. Now the issue is that if you only use that, there is no way you're gonna be able to absorb these in this, because this is not smooth enough, and you're gonna have terms that you have to use like something stronger than just the L2 norm if you hope to absorb them again. So the whole game is kind of to find a way around that, and so and somehow, I mean, this is a classical issue. Like there are many problems where you have some linear stability, like in the sense the second variation is positive, but then you don't know how to reabsorb the other terms, and you need to do something smart. Probably like one of the important examples that come to my mind is this Sobolev stability of the Sobolev inequality for p different from 2. There is that paper of Figali and Zhang where they have to do like they devise a very smart method to do that kind of stuff, to actually absorb the lower order, the supposedly lower order term into the stuff given by their second variation. In this case, it's much easier actually, much less technical than what they do. But basically what you have to do is, okay, this is positive, but if you just use this inequality, then you're dead. I mean, there's no way you're gonna control this. So you have to kind of split this thing in a smart way, like a part that will still be positive, another part where you don't use directly this inequality, but you use some kind of nonlinear thing to check that it compensates the part of the lower order terms that are not controlled by something like that. So this is like really ad hoc, like for this problem, the fact that we have a special form of the energy, then we can actually do something like that. And let me stop here. Well, I don't remember it right now, but basically you can do, I mean, this type of stability here, where is it, like this thing here, is basically because you can, I don't remember if you can fully diagonalize explicitly this thing, but basically you do a spherical harmonic expansion, except those are spherical harmonics for two forms, right? But still, spherical harmonic expansion. And so you find a spherical harmonics that gives you a negative direction, I think. So it's actually quite explicit. And now I don't know exactly what it is, but it's quite explicit. You mean that part here? No, here it's really, I mean, basically use the fact that you have some parts that are convex. So they give you, I I mean, okay, you have this constraint, so it's not really like a convex problem, but it's, I mean, if you know that Figali-Zhang paper I was talking about, it's always the same thing. Like somehow you want to use, there is some convexity somewhere that helps you, and it's not just like, okay, you look at this and this is something else completely unrelated, but you have some convexity that actually helps you, like, if you are willing to take away parts of the second derivative, then actually you have an inequality and you yeah. So it's really analytical. I don't have a geometric explanation. So what you can show, with degree 1, with Hopf invariant 1, I don't know. So of course, I don't have any explicit ones. You can always show in this, because this using like some kind of concentration compactness argument, this is in those papers by Lin and Yang, you can always show the existence of minimizers in a homotopy class. And so for instance, in the unstable part, like if lambda is small, then it means you will have another critical point that's not the Hopf map. And also you can play this game for any other values of the degree of the Hopf invariant, and then this will give you also other critical points. I don't know any more than that.